So the program of statistical mechanics is easy, right? Count up the microscopic states of a system to work out the partition function, take its logarithm, multiply by kt, get the appropriate thermodynamic potential, and minimize it to find the equilibrium properties of the system. So, of course, as always, the devil's in the detail, and we'll show just how hard this process is by considering the most simple case possible, which is that of a gas of non-interacting particles, the so-called ideal gas. We're going to work out the partition function for an ideal gas and obtain the pressure of an ideal gas from the change of the free energy with volume, and the entropy from the change of the free energy with temperature. We start by considering, though, the partition function for a single particle, and you may wonder, well, what's a single particle doing having a partition function? And the answer is that a single particle can exist in many states. So that's illustrated on this slide here, where I have written down the expression for the kinetic energy of a free particle taken from chapter 2, h bar k squared over 2m, where the allowed wave number eigenstates are given by 2 pi over L integer multiples of in the x, y, and z direction. So then what we do is write down the Boltzmann factor in these energies. This is some particular k sub n, and we sum these over all n, x, y, and z to find the single particle partition function. Carrying out this sum is difficult, but in the limit of a large number of particles, then we can approximate the sum by an integral, and we introduce the density of states, of k states per unit k, as derived in chapter 2. Here's the volume 4 pi k squared dk over the volume of an elementary cell in k space 8 pi cubed in 3 dimensions. So with this definition of the density of states in k, we can carry out the integral. The integral shown here. It's a standard result, and the resulting partition function for a single particle is shown here. It's actually interesting to derive something like this result, but a little differently. Instead of counting states explicitly, to ask what is the maximum number of particles that we could pack into a unit volume. Well, you're going to say that since the particles don't interact, that's presumably infinity, but that isn't quite true. So if we remember that the de Broglie wavelength of a particle is given by Planck's constant divided by its momentum, and we have an expression here for the momentum of a particle quantum mechanically, that it is h bar k, and we know that the energy is h bar squared k squared over 2m, then we can use this expression by setting the energy in one particular degree of freedom to be equal to a half kt using the equipartition theorem. So this is an approximation. And then substituting into this to find k, we arrive at the result that the thermal value, the value of k for particles of average thermal energy is given by mkBT over h bar squared, square rooted. So now, if we work out the de Broglie wavelength, which turns out to be just 2 pi on k, by substituting these two results here, and ask what is the volume of a box, a de Broglie wavelength of the particle of average thermal energy on each side. Well, that is lambda cubed. Here is our expression for k, and so that volume then turns out to be 2 pi all cubed times h bar squared over m pi kt all to the 3 halves. you'll see that's almost equal to the number we have on the slide obtained by doing the integral properly. And therefore, you see that the partition function for a single particle is just the ratio of the total volume to the quantum volume, which is a volume equal to the thermal de Broglie wavelength on each side. Okay, so now we have the partition function for a single particle. What about the partition function for n particles? One might think that this would just be the partition function for one particle to the nth power, because the particles are all non-interacting, and therefore we can arrange these. We can put the first one into any one of n states, the second into any one of n minus 1 states, and so on. Well, this looks good, but in fact it isn't true, and the reason is that the partition function involves this sum. So let's just take the case of two allowed energy states, E1 and E2, and write out the partition function. And now we have two particles, so we're going to square it. So we have e to the minus 2 beta E1 plus e to the minus 2 beta E2 plus 2 times e to the beta E1 plus E2. Because of the added terms then, the fact the terms are added together before the squaring takes place, we've over-counted, we've weighted by a factor of 2 instead of 1 the term in the partition function that involves having one particle at energy E1 and the second particle in a state of energy E2. To correct for this, we need to divide the partition function, this term anyway, by a half, or in general, divide the partition function by 1 over n factorial. Now there is a second complication in all of this, not illustrated by taking this case for two particles. What I have just said involves discarding these terms, and that's reasonable to do because e to the minus 2 beta E1 or E2 will be much less than a term in the sum of the energies. This is the probability of having two particles in one state, two particles in the second state. In general, when one looks at an expansion of the partition function for n particles, one has a probability that all n particles are in one state, that is this first term here, and that is definitely negligible compared with terms in which there is one particle in one state, because this n is on the order of Avogadro's number. But then there are other terms that involve having more than one particle in a particular state, maybe 10 particles in state 1, 3 in state 2, and so on, and they are also smaller than the terms involving just one particle in each state. So the dominant term in the partition function is then the single particle partition function that we just worked out, raised to the nth power and multiplied by 1 over n factorial. We will use this partition function to derive the properties of an ideal gas.